Good afternoon, everybody, and welcome to the NanoSeminars in the series of ICN2. As is practice in this series, we first of all welcome you and would like to share with you a very brief introduction talk to the topic in the general area of nanophotonics. So we have Dr. Martin Poblet of ICN2, who will give us an overview of some of the work he's been doing recently involving plasmons. So Martin, you have 10 minutes.
Okay, thank you, Livia. I will share my screen now. Okay, well, hello everyone. My name is Martin Poblet, and today I want to tell you about how a dielectric substrate can be characterized using plasmonic nanoantennas. I will start by defining what an nanoantenna is. Then we will see how coherent acoustic phonons can be generated from an optical excitation. This will produce a heating of the structure, and from the thermal relaxation and the coupling with the substrate, a transfer of energy towards the substrate will take place in the form of surface acoustic waves. And finally, we will see how to detect these waves, and I will finish with some conclusions on how different properties of the substrate can be characterized from the measured signals. So here we can see some examples of optical antennas, or just nanoantennas. These structures typically are in the hundreds of nanometers in size, and they are designed to give rise to confined electromagnetic fields when are illuminated. And they are structures that convert propagating electromagnetic radiation into localized energy and vice versa. And they are also excellent transducers of electromagnetic energy in mechanical energy, as we will see in the follows. When a metallic nanoantenna is optically excited by an ultrafast laser pulse, a photon-electron interaction is generated and a highly dynamic scenario is triggered. And from this electronic excitation, there will be a heating of the lattice that will produce a lattice strain, leading to a coherent excitations of the antenna's normal mechanical oscillation modes, which are known as coherent acoustic phonons. Here in these simulations, we can see how the oscillations of a gold rod of one of its normal modes are, in this case is the extensional mode, and these mechanical oscillations of the nanoantenna produce periodic perturbations in the dielectric constant that modify its absorption, as we can see represented in this graph, where we have an absorption spectrum for a gold rod for two different moments of the oscillation, and this absorption change can be evidenced using a probe pulse. So then the coherent phonos dynamic can be studied by pump probe measurements, where the pump will be the excitation pulse and the probe will measure the state of the antenna at a given moment, as we can see in this typical probe signal where the differential transmission was acquired. And in turn, due to the vibrations and the dynamic contact of the antennas with the substrate, mechanical energy will be transferred to the substrate, and thus the coupling of the nanoresonator with the substrate will result in the propagation of surface acoustic waves that will travel through the substrate, and which could be detected and characterized in the far field, in principle through the inverse phenomenon, that is the implementation of another plasmonic antenna as a receptor of these mechanical waves, which can be detected optically. And these mechanical perturbations will cause changes in the absorption of the new antenna, which can be detected also with a probe pulse. Let's consider a particular case of two horizontal gold rods separated by a couple of microns, where the first optically excited will act as a source of surface acoustic waves, and the second will act as a detector of these mechanical waves, as can be seen in this simulation. The antenna located in the center will be the source antenna, and then on its sides, there will be receptors antennas. So let's consider the case of the antenna located to the right. That will be this one. So we will have a configuration as seen in the inset of this graph, where the pump will be situated over the source antenna and the probe over the receptor antenna. And now, if we remember the previous signals that I showed, we can see that they are clearly different. And this is because the signal below is the product of an optical excitation. And in the above case, the nature of the excitation will be acoustic. Where the main difference that we have is that we will have a certain time until the antenna starts to oscillate now. In this case, it's pointed by T2. And this is the time that takes to the acoustic wave to travel from one antenna to the other. So then, if we know the distance that separates these antennas, the propagation of the speed of the acoustic waves through the substrate can be easily characterized. So now that we are capable of emitting and detecting these acoustic waves that are propagating through the substrate, if we could direct these acoustic waves, one could think, for example, of using them as information carriers. So, inspired by previous works who are using V-shaped antennas, they managed to direct light toward a particular direction. Something similar was thought for the case of the mechanical waves. So in this case, we used V-shaped antennas as source of acoustic waves, and disks as receptors of these acoustic waves, as we can see in this sketch. So we measured the differential transmission of the receptors antennas for different angles of the source, as we can see in these electron microscopy images. We obtained signals like the ones that we can see here for different angles of the source antenna. And then we structured the amplitudes of these measured signals and represent them in this polar graph, where can be seen that effectively the amplitude profile of the acoustic waves takes a preferred direction for the propagation. Here we have the differential transmission signals for different source and receptor configurations. And at the top and at the bottom of this panel, we have the optically induced signals for the V-shape and for the disk. And then at the right of this slide, we have the spectral content for each of these measured signals, where the vertical lines indicates the peaks for the signals due to optical excitations, which are the first one and the last one. And we can see that the peaks for the Fourier transform of the acoustically induced signals are shifted from the main frequency of the source. And why do I highlight this? Well, because if we consider that the frequency spectrum of the acoustic waves propagating through the substrate is equal to the spectrum of the source antenna, one will expect that the detection in the receptor antenna match in frequency with the source, but we could see that this wasn't the case. So assuming the hypothesis that the spectrum of the surface acoustic waves is equal to the one of the source antenna, then we proposed that the spectrum of the disk due to the acoustic perturbations will not only depend on the source antenna, but also will depend on the detector. So it will be a convolution between the spectrum of the source and the receptor. And in this way, we could predict the response of the receptor to the excitation of the surface acoustic waves in the time domain. And in the frequency domain, via the convolution theorem, we obtained that the Fourier transform of the signals detected due to an acoustic excitation will be determined by the product of the Fourier transform of each of the optically excited antennas. Here in this graph, we can see represented the Fourier transform of the optically excited signal for the source and for the receptor in blue and in orange, respectively. And the black solid line is the result of the product between the Fourier transform of each of these previous ones. And the dashed line is the average Fourier transform taken from the acoustically induced signals. And as we can see, we obtained a good agreement for what is proposed. So then, knowing the oscillation frequencies of the normal modes of the source and the receptor antennas, a selective detection of the propagating waves could be carried out. And that is, they could act as frequency filters, since these antennas are easily tunable. So finally, some conclusions to finish. PAN-Prof is a minimally invasive technique. Using antennas, we have the possibility of sending signals from one point to another on the substrate. We control frequencies and amplitudes, and without the need for any electronic conversion, taking into account the consideration that the detected frequency will be determined by the convolution between the spectra of each antenna. We can use them as frequency filters. And also by studying the behavior of the plasmonic receptors through the amplitude and frequencies detected, or the arrival time of the wave. For example, it is possible to study the losses, the speed of sound of the substrate, the coupling of the different modes to the substrate, and it's also a novel technique to study the adherence of these structures to the substrate. So that will be all. Thank you for your attention, and I will be happy to answer any of your questions.
Thank you very much, Martin. How are we doing for time? I'm just realized that I have a different time in my watch. Because we could take the questions together at the end, or we could take a couple of questions now, but you would need to answer them very, very briefly. Okay, so shall we take the questions at the end then, so together with the main after the main talk? And so I just say hi to Constanza, and I'll pass over to David Garcia, who is the host of Constanza. Right.
Thank you very much, Clivia. It's a pleasure for me to be back in this NanoSeminars, and it's also a huge pleasure to present you the speaker, Constanza Toninelli. Let me give you a few words about her and her career. She got her PhD at the European Laboratory for Nonlinear Spectroscopy in the topic of complex photonics and Anderson localization of light in the group of Professor Dielectric. And then she moved to Switzerland, to Zurich, to work with Bahit Sandokdar in quantum optics, in quantum photonics at ETH. 10 years ago, Constanza got her permanent position at the Italian National Research Council, the Centro Nazionale della Ricerca, where she established herself as an independent researcher, and she has established also her own research group. So today, Constanza will give us an overview of her research on quantum photonics with single molecules. And it's a pleasure. So Constanza, whenever you want. Let me remind you that if you have questions, you can write them either in the chat or in the questions and answers, and then we will let you speak up your questions. So please.
Okay, good afternoon, everyone. It's really a pleasure for me to give a talk at the ICN2. It's a pity that it's not possible for me to visit this time for a number of reasons, and I would have loved to meet you in person and to visit the different research activities at ICN2, and of course also to meet friends and collaborators over there. So I would like to thank in particular David and Clivia for the kind invitation. So if you agree, I would propose to discuss my recent activities on organic molecules for photonic quantum technologies. These are actually an orthogonal platform, I would say, with respect to the more conventional ones based on quantum dots or color centers in diamonds for the implementation of photonic quantum technologies of different kinds. And for this reason, I would like to focus mostly on their special features with respect to most traditional architectures. And one of them is the possibility to integrate these quantum emitters in complex three-dimensional structures, inspired, for instance, by the profile of our city center cathedral in Florence. Okay, so the way I recently like to describe my activity is with the words, just give me 1 second, I just wanted to add the pointer to make sure I have everything. Okay, awesome. Is with the words of molecular quantum nanophotonics. And the idea behind this is the vision that organic materials might contribute to the field of quantum technologies pretty much the same way they had a strong impact in optoelectronic devices. The reason resides mainly in the flexibility of the synthesis process that allows, on the one hand, to mass produce molecules at low costs, okay? And this is quite convenient. On the other hand, to tailor the electronic and optical properties and even magnetic properties from even ab initio calculations and in general during the synthesis process itself. Moreover, as I wanted to point out with this artistic cartoon, it is possible to handle molecules in the solid phase, in solution, and even in the gas phase. This portability makes the system particularly prone to the integration into pre-functionalized chips for a number of different applications, as mentioned here, from sensing to communication and even quantum computing. Okay, so we can really bring them in close contact with other materials in hybrid devices. Okay. To first approximation, our molecule, a single molecule, can be described by a two-level system with these two levels coupled by strong radiative transitions, which means that I can bring them in contact or in close proximity to suspended membranes of different materials, that I can use this molecule and its radiative transition as a transducer to read the local electric field or locally the temperature, for instance, as we will see in the rest of the talk, looking at either the emission frequency or the characteristic damping time of this oscillator, okay, this high quality oscillator. The possibility of isolating this quantum emitter, in particular in the solid state, allows us to transform, if you want, a laser beam, like classical light, into an exquisite quantum state of light. And that is a single photon Fock state. When we talk about single photon sources, what we have in mind, indeed, is a train of pulses containing one and only one photon per pulse. And this can be obtained just in virtue of the fact that we can address an isolated molecule, and then we can reliably excite it during the pulse. And after spontaneous emission, we will get a pulse with one and only one photon. Okay, so sensing single photon sources, and if we manage to push light matter interaction, and this is an important bit, to, for instance, even the strong coupling regime, okay, one can also use a single molecule to mediate the photon-photon interaction. Indeed, photons are ideal carriers of quantum information, right? And we can encode information in different degrees of freedom of the photons, time being or polarization, etc. But when it comes to realize logic gates, we have troubles because photons are non-interacting particles. And if you want to have a gate, then you need to have interaction. In other words, you need to have high nonlinearity at the level of single photons. And we don't have materials with such high nonlinearity. However, if we manage to push light matter interaction at the strong coupling regime, we can then use the molecule as a mediator of photon-photon interaction. Okay, you will see there is actually a twist to it. We can also overcome this problem by using some symmetry rules in the commutation of the creation and annihilation operators for photons. Okay, so this is a very general introduction, but what does a molecular quantum nanophotonic group look like, lab look like? Well, we typically start in a small chemistry lab with the fabrication of our molecules, and we have them embedded in crystalline matrices of different kinds. The important point is that we can control the density of molecules inside each of these nanocrystals, for instance, okay? So this allows us, for instance, to do a number of different experiments, as I said, from single photon sources to more let's say, more complex studies, for instance, about cooperative effects or collective effects. Second step, in a small nanofabrication lab, we are able to embed molecules into different kinds of photonic structures, okay? And you will see some examples about that. Actually, the whole characterization is performed at cryogenic temperatures typically, and there's a reason for that. That will come in a minute. Our core business is actually that of single photon sources in general. And the overarching goal for people working with single photon sources is the possibility to scale them up, okay, providing say an array of single photon sources for quantum optical networks. Okay, these are paradigmatic setup, I would say, for photonic quantum technologies of different kinds. So an optical network is behind say the so-called quantum internet, is behind boson sampling type of experiments that have recently shown quantum supremacy. It is also the setup somehow behind linear optical quantum computing protocols, okay? So what you want then is to have your source delivering a photon in one of these modes of the network, your molecule delivering a photon in one of these modes. And there is a problem actually with the current technologies. So why do we really need to push this quantum emitters business farther? Well, the workhorses in these domains are sources based on parametric down conversion or other probabilistic effects in non-centrosymmetric crystals, okay? This type of generation processes, they do not change the photon statistics. That's the first message. So you start with Poissonian laser statistics, and afterwards you get pulses, maybe photon pairs, where the photon statistics is again Poissonian. The advantage there is that you can use, in the end, one pulse of the couple to herald the presence of photons, of the twin photon in the other part of the pair. However, since the photon statistics is still Poissonian, if you want to get just one photon per pulse, you have to decrease the overall fluency, so the intensity of this beam, to a level that implies that the probability of getting one photon is of the order of 10 to the minus 4. Moreover, you don't know when this process happens, which means that if you are cascading in an array, as I mentioned before, for your optical linear network of 6, for instance, modes, you expect to have coincidence rates of the order of 1 per year, which is quite impractical, okay? So that's why we're all very much interested in quantum emitters, because there instead, the process, the generation process is deterministic, happening on a sort of push button principle. And whenever I want, I get one photon out. In practice, this is a bit more complex than that. And indeed, you have to characterize your single photon source in terms of the efficiency, because this, of course, depends on, for instance, your probability of collecting the photon emitted by the molecule. You might have non-radiated channels kicking in, etc. The other important figures of merit for your single photon sources are the purity, which accounts for the probability of having multiple photons per pulse. Okay, this is something you don't want for certain application, for instance, for quantum communication, where this immediately entails, let's say, opens a door to your cyber attack. Finally, what we also care about is the ability of the emitted photons to undergo two-photon interference. This is actually the only way that photons have to interact one with another. Consider, I mean, I'm just now, I don't know, maybe everyone knows about it, but I thought that, I mean, I might give really a very introductory first part, and then we'll go more into the recent research. But I would like everyone to follow. Okay, so imagine you have the following experiment. You send two single photons, Fox state, at the input port of a 50-50 beam splitters. So classically, you have four possible outcomes of this simple experiment. Both photons are transmitted, both are reflected, or one is transmitted and one is reflected. Each of them would occur with a probability of 25%. So the event of both detectors at the output port of this beam splitter clicking is expected to occur with a probability of 50%. Now, due to the interference among the probability amplitudes of these two processes, we actually observe a photon coalescence. That means that both photons want to leave the beam splitter from the same output port. Okay, so this the simultaneous clicking does not happen. And this is a totally an exquisite quantum effect. And you see that somehow it is equivalent to a photon-photon interaction, because the presence of a photon in the other branch changes the optical properties, or the reflectance, if you want, of the beam splitter. Okay, so based on this very simple effect, all linear optical quantum computing, Bell state measurements, entanglement-based QKD protocols are built all on this very simple concept. However, this is not totally trivial to achieve, especially for emitters in the solid state, because the emission of indistinguishable photons sets some stringent requirement on the photophysical properties of the emitter. And in particular, the radiative transition should not suffer from dephasing due to, for instance, the interaction with the surrounding phonons, okay? This is typically traced by means of excitation spectroscopy, in where we can measure the line width of the transition that should be limited only by the lifetime of the excited state, okay? So this is what we are looking for, like one and only one photon per pulse, and these photons should undergo two-photon interference. Okay? This is what we are asking our molecules. So I will give in this talk a quick a quick introduction about the quantum optics with single molecules, and we will then see what are their special dishes they offer that I briefly outline here. First point is that molecules are nominally all identical, okay? And this is very important. You remember this goal of scaling up the number of quantum emitters. If these photons have also to be indistinguishable, you'd rather want these molecules to be identical. And if you compare them with the epitaxial quantum dots, it is clear that it is much easier to get identical emitters with molecules than with artificial structures, right? And again, molecules are portable, and we can bring them in close contact with different type of structures, which brings me to three proof of concepts application in different domains, starting from metrology, QKD, and sensing. And I will end the talk discussing our path to integrated single photon sources. In particular, which type of molecules am I talking about? For these applications, we are considering polyaromatic hydrocarbons. These are very small molecules that are planar and rigid. And this is very important to decouple from the phonon bath, in a sense. They possess optical transitions ranging from the visible to the near infrared, and starting from solution, as I said, we embed them in nanocrystals or in crystals of different kinds that have the role of shielding oxygen diffusion, which means that these dye molecules, they do not photobleach. So we can work with them even at room temperature for several hours, and at cryogenic temperatures of 1.4 Kelvin, we study the same molecule for months and even years. So sometimes we give them names, right? So here I need to stop, right? I mean, this has to be clear to everyone. We're not talking about the sort of biomarkers that photobleaches immediately. This is a different kind of molecule that's embedded and that survives over many fluorescence cycles. The optical properties are given by the following Jablonowski diagram, in which you see we have singlet states and triplet states, the transition among which is typically forbidden in dipole approximation. However, due to spin-orbit coupling, typically you do have a residual intersystem crossing rate that can be as small as 10 to the -4 for the proper choice of guest and host system, such as in this case of dibenzotyrrolene molecules embedded in anthracene crystals. This is the system that I study the most. This means that we also have quantum yields, so the probability of a radiative transition is very close to 1. This transition here, the radiative transitions, are actually into different phonon lines. You see these different green arrows, they correspond to different transitions to different vibrational ground state of the vibrational states of the electronic ground states, okay? However, there's only one of these lines that is potentially lifetime limited, delivering indistinguishable photons. And this is the so-called 000 phonon line, this red arrow here, that implies no phonon exchange, not even within the molecule itself. At 3 Kelvin, this has a branching ratio of 50%. That should be compared, for instance, with 4%. That's the case of the zero phonon line of nitrogen vacancies in diamond, okay? So that's very convenient, and that can also be modified, for instance, by coupling the molecule resonantly to an optical cavity, exploiting Purcell enhancement. Excitation spectroscopy is what we use to measure the line width of this zero phonon line, and this is what you're looking at in this GIF, where you observe, you're looking at the red-shifted fluorescence as a function of the exciting laser frequency. The crystal contains several molecules that have a slightly different frequency because they feel a slightly different local environment, and that's why they pop up at different moments in time. Now let's focus on one of these spots, which is a single molecule, and you can reconstruct a nice Lorentzian curve that corresponds to a lifetime limited line width of about 40 megahertz. So that's really lifetime limited. We might really get indistinguishable photons. So we are like having a sort of two-level system in the solid state. And it is very narrow, this transition, which is relevant because this matches very well the bandwidth of atomic quantum memories. Okay. Now let's talk about purity. So the probability of having multiple photon per pulse. How do we measure that? This is accounted for by the second order autocorrelation function, which in simple terms measures the probability of a detector clicking after another detector has clicked at time 0, okay? So in practice, we need to set up a Hamburg-Brown twist experiment where the photon stream is split in two in order to compensate for the detector dead time, okay? However, what we expect for an ideal single photon source is that the probability of having both detectors clicking at the same time should rapidly drop to zero, right? Because they cannot come together. And here you see how this relates with the multiphoton probability. Different pumping schemes we can adopt. In this case, for instance, we show in this Henry-Brown twist experiment, we were pumping on the 00 phonon line and collecting the red-shifted fluorescence here, which is in this gray shaded area. And here you see the nice suppression of the second order correlation function in zero, the so-called anti-bunching, okay? Which means that really we have almost zero probability of getting both detectors clicking at the same time. Now, as the second order correlation function essentially measures the rho to 2, so the probability of being in the excited state, if we drive the system strongly, resonantly, we can observe the famous Ribby dynamics, which is possible thanks to the long coherence time of this superposition state. In practice, we do not want to get rid of the zero phonon lines because those are our indistinguishable photons. So we typically use a different pumping scheme based on the excitation of a vibrationally excited state, followed by a fast non-radiative transition to the vibrational ground state of the electronic excited state. In this way, we can, with a notch filter, collect only the zero phonon line. And another detail, we would rather use pulsed excitation because we want to trigger with the laser pulse the emission of the photon. Really, only in this way you can really benefit, in a sense, from having a single photon source, because you know when the single photon is coming. Also, in this case, you see that there's no peak left at zero due to anti-bunching. Okay, well, really the purity of these sources is high. What about two photon interference? Okay, we saw potentially lifetime limited transitions. Can we measure two photon interference? And how is this done? Okay, so here is the beam splitter that now looks different because it's a fiber coupled beam splitter. And we want to send photons at the two input port of this beam splitter. We start with a single molecule. So what we need to do is to split the stream of photons, the train of photons, into two arms. And we use for this a polarizing beam splitter cube. And then the relative ratio is adjusted with the polarization controller. We have these two branches, and two like technical details are the following. So we have to add a delay line on one side in order to lose track of the temporal correlations between the two train of pulses. And second, we have a polarization controller on the other arm. We need these because we want to provide the visibility figure of merit in this interference experiment. And if you want to give a visibility, you typically need to compare the interfering versus the non-interfering case. And this is done by switching between orthogonal, stands for orthogonal, and parallel polarization. Only in the case of parallel polarization, we do expect to see two photon interference, which again has the same shape, let's say, of a deep zero time delay, which means that we do not register this kind of effects of both detectors clicking at the same time. This is the first experiment we did, and that was done in CW excitation, which is actually a bit easier. And you see here is the visibility figure of merit, in which we compare the G2 in zero for orthogonal and parallel polarization. And here you see we had, in the end, simply, we expected for two single photon sources a G2 in zero of 0.5. If you don't have interference, if you do have interference, this curve is brought down to zero. And this has a visibility of 91%, just looking at zero. But we're not happy with that. We really want to have zero integrating like during the entire pulse duration. So we switched again to a slightly more complex setup and to pulsed excitation. And again, we could claim a visibility of the order of 90%. And this time, this is obtained by integrating and comparing the area of the peak under 0 time delay. Okay, so this whole discussion makes molecules really very good single photon sources. These whole very technical slides, you can skip it, just for me to remember saying that, okay, we have also prepared a model, okay, to rigorously describe the Hongu-Mandel two-photon interference experiment. And this requires also the independent estimation of many parameters, including the lifetime, the G2 in 0, so the purity of the single photon source, the line width, the delay in the Mach-Zehnder interferometer. If you want to say something from your measurement, you have to independently characterize all these. But now, having done this, what I can say is that, you remember, we have this visibility that's limited to 90%. And now what we can say is that this is really due to a residual dephasing, which is present in our emitter, due to the temperature that's not low enough. Okay, we work at 3 Kelvin, whereas the system would be really lifetime limited only at 1.4. Okay, so we need better cryostats. Okay, which other features would you like your single photon source to have? One thing is the tunability. Okay, you want to be able to move the 0 phonon line frequency. And now we start to, you know, pick and place our emitters in different functional devices. So the effect we exploited here was the, voltage-induced Stark shift, okay, of the molecule 0 phonon line. So actually, we're talking about a molecule that's centrosymmetric, which means that it doesn't have any permanent dipole moment, and hence this voltage-induced shift is to be ascribed to a second order star shift, which means it's not huge, and which actually means also that the transition frequency of the molecule is stable, because else it would suffer a lot from the surrounding noisy charge environment. We wanted to be fancy, and so our electrical tuning was demonstrated in this case using as transparent electrodes, two-dimensional materials that allowed us to make a sandwich with the molecules inside, and to have a very tiny condenser, which means that we could drive the frequency of this molecule very rapidly. And we could tune it over the entire inhomogeneous broadening. You remember we had these molecules popping up at different moment in time, and we could kind of tune them all over the inhomogeneous broadening. So, okay, so let me move on, and then I'll stop later. I don't know how am I doing with time, but I suppose I can still move on a bit. That was actually the Stark shift is a method that's used also for quantum dots and for NV centers, color centers in diamond in general, silicon carbide, etc. We accidentally discovered something new, and that you will see was quite powerful. Okay. Independently in two different labs, in my lab and in the group of Michel Horry in Leiden, we had the same accidental discovery, and then we happened to discuss it. And this is the following. So we were actually shining the molecule with an additional laser, okay, with respect to the one that we used to investigate its excitation spectrum. And we saw that as a function of the illumination dose, the 0 phonon line was shifting in frequency. Okay. We repeated the experiment many times, and then we had two main tasks. Okay. The first one was to understand the reason behind this optical tuning, and the second one was to calibrate it in such a way that we could use it to do something good. So there's the reference in the following slide. The idea we had is based on the photoionization cascade that creates long-lived charge states inside the matrix. So there's not just the molecule, but also a role of the surrounding anthracene molecules. These long-lived charge states result in a field buildup that, due to second-order star shift, moves the molecule transition frequency. I was then crazy enough to ask people working with me to use this to demonstrate the possibility to tune into resonance different molecules on the same chip. Okay, that would be very powerful because you cannot do with the electrodes, you don't have the same spatial resolution, right, that you can have with a laser beam. And imagine, moreover, if you want to integrate molecules into photonic structures, how would you then put on top of that also electrodes with and apply a slightly different electric field in our optical network paradigmatic system. So I asked them to perform this experiment, and these are the results. So we started with 5 emitters that were within 20 microns about and 20 gigahertz apart. This is how the famous movie looks like. So it's now speeded up by 6 times, and you see again this popping up. After tuning one by one, you see that all molecules spectra are within twice one line width. Okay, they are now brought all together, which with this movie means that they are now, there's a moment there for which is kind of this one, in which they light up all together. So this is a multiple emitter experiments, multi-photon experiments that cannot be done with any other type of quantum emitters. So, I mean, I was happy enough, but I was not totally satisfied. And I asked them, is it possible to use this to do 2-photon interference then, but for photons coming from distinct molecules this time, after having tuned one on top of the other? And this is what we then headed to. So here on the right, you see the sequence of pulses that we used in order to tune these molecules that originally were 2 gigahertz apart, and in the end they were one on top of the other. And this is the optical setup. You have 2 molecules that were very close by, like in the setup. So we had to kind of split the setup in 2 and have 2 excitation laser and separate the fluorescence with the D-shaped mirrors into 2 optical paths that were coupled to the single mode fibers at the 2 input of this fiber beam splitter. And to make a long story short, this is the result of real-time Hongo-Mandel interference. This is the name of 2-photon interference in jargon. And where you see that the peak in 0 is again depleted due to an interference effect for photons coming from distinct molecules. You see, it is less clean than the case of single molecule, and this is due to the fact that the visibility is lower, it's 40% instead of 90%. And what is that due to? Again, thanks to our model, we could understand that this is due to a residual drift that we have after having them tuned one on top of the other. Okay, if we switch off the tuning laser, the molecules are still kind of stay there, but the relative frequency between the two starts to drift. We could also, again, measure as a function of the tuning to photon interference that shows the characteristic quantum bits that you can observe in this figure. How am I doing with time? Just to know, because I don't want to.
Very well, Constanza. I mean, you can really take.
Okay, I can relax.
Yeah.
Okay, so what about brightness? You remember, I mean, how many photons do we actually get at first glance? You would be surprised to know that if you don't do any photonic streak from a single molecule, even with the radiative quantum yield of 1, you get about 5% of pulses with 1 photons. And this has to do with the emission pattern. which can be calculated and also measured by imaging the emission in the backfocal plane that contains information about the power distribution in momentum space. We're not dealing with the dipole in free space, okay? We're dealing with the dipole that sits on top of a glass cover slide. And hence, most of the emission is funneled at high angle beyond the critical angle between air and glass, actually. And this means that, especially if you work inside a cryostat and you have limited numerical aperture, you collect very few photons. So how could we improve our emission pattern and hence the collection efficiency? The first idea, was inspired by the Yagi-Uda antenna designed at radio frequency, okay, in which you have these metallic elements and there's a feed element that induces oscillations in all the other metallic elements, and the constructive interference among the radiation pattern builds up in the direction of the observer, okay? So we have translated these two optical frequencies, which means, much smaller distances, and we made it planar, okay? Because in this way, we could actually address multiple molecules at the same time on the chip. Moreover, we relaxed totally the accuracy in positioning. Okay, there was a previous work about that, and if you want, we can discuss about it. But I mean, there's not much time in. Don't want to focus much on this work. The concept again is that of constructive interference among the image dipoles induced onto these two metallic elements, this gold reflector and this gold director. So if you do the design right, you get this angular emission pattern, as you can observe in this polar plot, that's mostly confined within 24 degrees of polar angle. So we did the calculation and we also did the experiment, embedding our molecule between these two gold layers. And here you see the measurements that matches quite nicely the theoretical calculation, where you see that how the emission pattern was totally modified thanks to this trick, which brought our collection efficiency from 2% to up to 90% with small numerical aperture. Okay, that's actually one thing that now it is done in different labs around the world. Now maybe there's some time for questions before I move on to the applications.
Good. So so far we don't have any question for you, but okay, let me warm up the thing and maybe people get animated. So I have a general question for you. When you show your scheme for a lab working on quantum photonics with the molecules, you show that there is a part of chemistry, no? Mm-hmm. So people working, for example, with self-assembly quantum dots, they get the material from somewhere else. Yeah. No? But you could have research on chemistry, and I guess that's a whole world. Do you do that? Do you really have an activity on that, on the meters?
That's a very good question. So, I mean, currently, there are at least, there are several levels, let's say, of chemistry that you can do. I do the super simple one. I mean, I buy the molecules, but I grow the crystals, okay? And there is already there some knobs that I can tune in the crystal growth in terms of quality and in terms of density and in terms of, for instance, emission wavelength and in terms of even the polarizability. I mean, some properties are really determined by the type of guest host system and how you put them together. So there are some knobs that are, I mean, at these high level, let's say chemistry, high level in the sense of, and then there is of course, like let's say a huge potential related instead to the synthesis. Mm-hmm. Now I am leading a European project in which we do have also a chemistry group where they have been working on the synthesis of different compounds, for instance, targeting emission to longer wavelength, 1.5. Okay, 1.5 microns, or you might want to target, I mean, other aspects, okay, that you can, I mean, this is to say that there's a huge potential. People are working on that. The community is not huge, and I have to admit that there's a technical difficulty in this case, which is related to the fact that these molecules, in particular these polyaromatic hydrocarbons, are very poorly soluble, okay, okay. Which means that they are a bit a nightmare for chemists, okay, and so typically the purity of the compound, they're not happy because the compound is not pure. I tell them, look, I mean, I just need one molecule in the end. Yes, I mean, so in the end, for me, the purity of the compound is not so important, but still. So it is true, and I'm trying, and I've partially managed to convince chemists to work on that. And now I have submitted another project in which there's a strong involvement of chemists, for instance, for the synthesis of molecules that have a non-zero spin in the ground state for the development of spin photon interfaces. Yeah, this would be totally, you know, additional line of research that I would like to pursue, and that depends. And there's some movement around that, about that.
Good. Okay. If there's no questions now,
okay,
we can then move on maybe.
Okay, yeah. Okay. So let's talk about possible applications, because at some point you start to be bored about mentioning these applications only in the introduction to your papers. You really want to show that you can do something with your single photon sources. The first one might be surprising, but has to do with metrology. So if you imagine this train of pulses with one and only one photon per pulse, this is actually the ideal way to define an intensity standard, okay? Just counting photons, okay? For instance, the novel candela could be simply the intensity, okay, of a DBT molecule with this setup, okay, after a certain number of cycles. Okay. The optical properties of our system were good enough in terms of count rates and narrowband and purity to convince people from PTB to come over, which is the German Metrology Institute, to come over to Florence to try using our molecule as intensity standard. The first thing you typically do in this metrology chain, as I learned, is not to use your molecule as a primary standard, but as a secondary standard, which means essentially that you use your molecule to calibrate a test device, this single photon avalanche photodiode, against an analog diode that was previously calibrated in Braunschweig against the primary standard. Okay. So the fact that you can have a high count rate from your molecules means that you can use this as and in a narrow frequency band as a secondary standard. So this worked nicely. We did this calibration, and now, I mean, that was published, and now we are instead aiming at in another European project to use really the molecule as a novel intensity, to propose it as a novel intensity standard, of course, talking about low light levels. Now, the second application that we have recently published is for the in QKD. Okay. So we encoded information in the polarization states of photons, and we used the BB84 protocol to exchange the key between the two parties, the famous Alice and Bob. At this stage, we essentially have characterized the channels, which means that we have measured the quantum bit error rate, which means essentially what's the probability of measuring one polarization once you have set the orthogonal one, for instance. And we have compared these results with respect to the state of the art, okay? The state of the commercial state of the art for QKD protocols is based on weak coherent pulses, which are attenuated lasers. if you compare the Kuber that we measure with weak coherent pulses and with a certain, let's say, probability of getting 1 photon per pulse with the laser with respect to the case of single photon sources and molecules, you get a better Kuber, okay? And this is because we're now talking, sorry, I forgot to say that, about a room temperature experiment, okay? We wanted to do room temperature experiment because this would set us apart from everybody else, in the sense that other similar experiments done with, for instance, quantum dots, they really require low temperatures. There's no room temperature emission. Whereas for practical application, imagine you want to send your single photon source with a satellite. If you can do that at room temperature, that would be very convenient. So if we are working at room temperature, though, we have the problem that the spectrum is much broader. And if the spectrum is broader, all the polarization optics that we use to set the state and in detection, they are more less precise, right? Because they are optimized for a given frequency. However, due to the different photon statistics that's offered by a single photon source with respect to the laser beam, the secret key rate that we can measure is already better than what you can get with this yellow line. That's the case of weak coherent pulses. Now, a lot of work has been done, however, on weak coherent pulses in the development of dedicated protocols, and in particular, they employ typically decoy states. And so if I compare now our single photon source with the secret key rate that you can get with decoy states, this is this red line, and you see that there's still kind of 1 order of magnitude, a bit less maybe, that we have to improve our molecules in order to be competitive. However, this gray shaded area refers to what we expect if we manage to push our efficiency in the collection of single photons from 8% to 30%. And you have seen we can do that, okay? We didn't do that because this was the first experiment, so we just had 1 gold mirror, as you can see here. But you remember we can really funnel emission into a narrow cone. So we expect to be able really to already be competitive with state-of-the-art devices for QKD using room temperature single photon source. Now, the third application I wanted to mention is not based on molecules as single photon sources, but rather as nanoscale sensors. And this work is done in collaboration with David and Clivia at ICN2. And I'm super excited about already our preliminary results, and can be really like a new research line which triggered by these results. My standpoint in the study of the interaction between the molecule and the phonons is actually that of, like photonic quantum technology person saying that phonons are a problem, okay? So I want to get rid and to decouple from them. And the molecule is coupled by means of vibronic coupling to the phonons of the nanocrystals, which in turn is coupled to the surrounding phonon bath, okay, of the environment. So we wanted to study this mechanism further, and the first experiment, I mean, I'm very glad to be able to speak after Martin spoke, because he gave an introduction about different mechanisms really to image and to measure acoustic wave propagation. And this is actually a very similar experiment, although this is done again at 3 Kelvin. Okay, this is like sort of totally different range of temperatures, where probably things would behave differently. Okay, so here we have we managed to deposit our nanocrystal on top of a nanostructured membrane coming from ICN2. And we wanted to see whether the molecule could sense the phonon propagation occurring in this on this membrane, and we had to excite phonons there. And for that, we used a laser source, essentially, that we could displace with respect to the molecule. This vibronic coupling is such that if the molecule sends a higher temperature, its excitation spectrum, its zero phonon line broadens, okay? And this broadening can be calibrated and has an exponential dependence actually with temperature. We can discuss this in details, okay? So these are the results we got after calibrating the molecule, where you see that, I mean, the position of the nanocrystal was not symmetric with respect to the membrane. That's why you actually have this non-symmetric temperature profile. And the take-home message here are two. The first one is that we have access to temperature in a range which is unusually low, let's say from 4 to 10. I don't know how many other methods exist to measure temperature in this range. Really, please tell me. We are just ignorant at this stage. We can do that with a high resolution, spatial resolution, and we can even learn something about the phonon propagation. And indeed, this analysis was done in collaboration with Professor Hilke at McGill University, who's visiting in Florence. So we try to fit this data using a solution to the heat transfer equation. And these dark blue lines correspond to a constant thermal conductivity. And you see that by no means they manage to reproduce our experimental data. So we made the hypothesis of a polynomial dependence of the thermal conductivity with temperature. And you see that with an exponent of 0.5, we could perfectly, let's say, we could get qualitatively at least a good agreement with respect to the experimental data. So we can measure temperature in a weird temperature range and a low temperature range on a suspended membrane, and we can learn something about heat propagation. Okay, so that's, I think, already quite powerful tool that has been demonstrated. I'm curious to know what you think about this thermal sensor. Okay, now just the very last part of my talk would be dedicated to our path to integrated quantum networks. Why do we want to put molecules inside a integrated photonic circuit? Well, my take to this is that if you want really to scale up the number of quantum emitters on chip, you cannot afford really like a free space type of operation, and you really would like to have a miniaturized integrated photonic chip. This is also a way to minimize losses and to have different functionalities all on the same ground. Okay, this is then why we want to do that. The first attempt we did was based on a theoretical paper, 2011 by Jesu Kwang, which suggests the possibility to use the coupling to deposit an emitter in close proximity to a ridge waveguide and exploit the coupling to the evanescent tail of the electromagnetic field leaking out of the waveguide. Indeed, the coupling efficiency, which is defined as the emission in the waveguide with respect to the emission, the total emission rate, depends by the group velocity, of course, but is accounted for by an effective area, which takes into account, on the one hand, the intensity at the emitter position, and on the other hand, how well you can shrink the electromagnetic field. So you can find a trade-off in the thickness of this waveguide such that this coupling efficiency is high enough. Okay, that was a kind of the simplest approach to integration, although in the end it was not so simple. So we deposited spin-coated crystals this time on top of a silicon nitride waveguide. We selected molecules exploiting confocal scanning techniques that were in close proximity to the waveguide, and when we imaged the entire fluorescence from the entire chip. So by comparing the relative intensities in this spot that corresponds to essentially the residual free space emission and the single photons that have instead been funneled inside the waveguide and scattered at the output couplers, we could estimate a coupling efficiency of 40% that comprises both direction of propagation. Okay, so that was very good because the design, the architecture is quite simple. However, the bad news is that this is more or less as much as you can get with evanescent coupling, and this is not enough if you want to scale up. Moreover, we have been involved in a number of different experiments, like beyond this one that I just showed, in which the coupling two trenches, plasmonic waveguides having slits, some papers not from other groups, and all of them, they reported about, I mean, coupling efficiencies, some low temperatures, some room temperatures, but all never higher than the 40%. So we really have to think about something new, something different, and that's why we have conceived this idea of molecules in nanocrystals, because they would entail a number of different integration strategies. For instance, you can imagine to disperse your nanocrystal in a polymer photoresist and then use direct laser writing to draw a structure around the selected emitters. Or you can use electron beam lithography and such sacrificial masks to couple to other structures, for instance, carved in silicon nitride or other semiconductor materials. So we developed our own the reprecipitation technique to get these nanocrystals. Maybe there's no need to discuss these in details. One point, and the nice thing is that now everybody is doing nanocrystals, everybody working on molecules like these nanocrystals. And that was not obvious because if you consider, for instance, silicon vacancies in nanodiamonds or in general quantum emitters in nanocrystals, they typically suffer from spectral diffusion. And the reason is that your quantum emitter will be very close to the surfaces, and surfaces are typically a charged environment which is not quiet. So for the same Stark effect that I mentioned earlier in the talk, this implies that you have so this charge noise is translated into spectral diffusion of your zero phonon line, as here evident in this paper on silicon vacancies. This is the same measurement done for 1 hour excitation of our DVT molecules inside nanocrystals. And you can see that they are stable over 1 hour. Again, very lifetime limited line with extremely pure single photon emission. Okay, that's why people like it. And we have really started using them to integrate them in photonic structures of different kinds. One project we had was in collaboration with ICFO, in which we deposited by a microinfiltration setup our nanocrystal in a small hole, and then we used the electron beam lithography kind of to cover this hole and not have nanocrystal all over the places. And already you see that there was some, this is the nanocrystal doped with many molecules. This time it's not a single molecule, and we had fluorescence also here at the outcouplers. But what I like most is the idea of three-dimensional structures, okay, and that you can achieve by means of two-photon polymerization with direct laser writing. Okay, why do I like it? First, it's because it has a huge flexibility in terms of the structures that you can imagine, and you can even imagine to have a inbuilt fiber coupler and very complex chips. You can have a treater, for instance, instead of a simple beam splitter, you can have a three-dimensional treater and study multi-photon interference, which is totally new topic of research. And the other point is that you can have your quantum emitter not in the evanescent tail, but now this time where the electromagnetic field has its maximum. And so expecting a much higher coupling efficiency. So we tried this out already. And you see, we have fabricated 3 different structures, the microdome, a microdome on gold, and a suspended waveguide. Fluorescence was preserved after the entire fabrication process, which involves also the use of solvents and so on. That was not obvious. And moreover, okay, we did the morphological characterizations by means of atomic force microscopy to make sure that the roughness were low enough. And with the microdome, for instance, we could already obtain a factor 12 enhancement in the collection efficiency with respect to the bare crystals. Okay. The overall emission pattern was good enough to obtain 50% coupling efficiency into a single mode fiber. That's also quite important. And finally, last but not least, the optical properties, including the photostability, was preserved after the entire process was carried out. Okay. So now we are working let's say on expanding these tools to different type of designs. Honestly, we're having troubles with our nanoscribe machines. That's slowing us, unfortunately. But I really think that the concept is extremely powerful. With that, I would like to thank all the collaborators and all abroad and people that made these all these experiments possible. I would like to advertise the PhD and postdoc positions that are available in my group. So please kind of just drop me an email if you want to know more. We already have a Spanish girl working with us. And I'd like to conclude with another advertisement to join us in this workshop that's going to take place at the beginning of fall in Erice. That's a wonderful location, and the list of speakers is really astonishing. Now, actually, you can just go to this website that was done by David, and registrations are open, and we really look forward to meeting you in Sicily. Thanks for your attention.
Thanks a lot, Constanza, for this wonderful seminar. If you, so far there are no questions, but there is a question for the first short talk by Martin. So we will give time for people to prepare questions for you. So I'm gonna allow to Diego to make the question himself.
Thank you for your nice talk, and also Martin for those results about the electron phonon generation with plasmonic nano antennas. I had a question about the strength of that effect. So how strong is the generation of phonons in these plasmonic nano antennas? And
Hi, Diego.
The resonance, and also if it will be visible with a standard continuous wave laser.
Yeah, I am not sure what do you mean with strong, but I will say it's one of the main decay mechanism after the excitation of the antenna. Let me see if I can share the screen again, and I will show you with the signal. For example, here we have an exponential decay that will be the thermalization of the antenna, and the phonon frequency, the phonon amplitude is quite big if you compare it with the excitation pulse. I am not sure if you mean if you refer to that strong.
Mean in the figure above, how much it displaces the plasmon resonance?
Here is between 10 and 20 nanometers in this case. It's quite dependent of the size of the antennas, and this kind of structures are really easily to tune, and the frequency is quite easy to manage with the size and the height of these structures. So in this case, it's between 10 and 20 nanometers.
10-20 nanometers with 8 gigahertz phonon frequency.
Yeah, for this case. But in this case, what we did in this work, we excited the antenna using the pump tuned at 400 nanometers in an interband excitation of the gold. And then we detected with the probe tuned at 800 nanometers. So in this way, it's easily to separate the excitation and the probe.
But it will happen in principle also at the optical frequencies, or it diminishes the effect?
I don't know, actually. I will guess, the optical frequency also will happen.
Okay, thank you. Very interesting.
Thank you, Martin. So I don't know if we have any question on the Constanza's seminar. I understand that these online seminars are convenient because we reach people that are distant but are not the best place to discuss things. Now, I have a question actually about the experiment on the thermometer at a low temperature. You show that you cannot really reproduce your data with the standard heat equation, and I don't know if that means we can push it far and say that at these very low temperatures there's something weird happening in the thermal transport, or is still
I mean, as far as I understand, but I really have to to go farther in the studies. It is not obvious that the thermal conductivity should be constant with temperature on such scale. Okay. So we can expect to have some thermal dependence. I don't know. I mean, the goal now is really to further develop a microscopic model. Yeah. To understand what's going on and what is inducing this dependence of the thermal conductivity on temperature. I mean, I think this is really interesting, and and as I said, I'm not sure whether there are alternative ways to spot such an effect. And I have to say that this calibration of the temperature was obtained taking into account the literature concerning the, that takes into account the thickness of the membrane and the presence of holes. But I mean, at the moment, there's no interference effect. Let's say there's no phononic band gap taken into account. So, I mean, definitely this would be a further complexity in this system.
Okay. I don't know if we have any questions. Yeah, we have an attendee. Diego also. I will actually let him panelist so he can open his
camera.
His camera. All right. So how it is. Yeah, I think he should be able to.
Okay.
Yeah. Now, yeah.
Well, I think I open in the device. I have no camera, so.
Okay.
Anyways, hi, Constanza.
Hi, Diego.
I also have questions about this part of the talk, which I find fascinating. This experiments on the membrane. I'm not sure if I understood correctly, but you measure this temperature by the line width increase due to the electron phonon coupling. Is that correct? Or
allora, what I measured was, I measured the line width increased as a function of the laser position, okay, the heating laser position. I mean, it's a very similar, like curiously similar experiment to what we have seen by Martin, actually. So he had like a heating spot, and the nanoantenna. In my case, there's no nanoantenna, but there's still some absorption going on there. And then there is, and the molecule is a pickup, let's say, of phonons and measures the temperature as a function of the laser distance. This temperature dependence of the line width was previously calibrated. Let's say that I was artificially changing the cryostat temperature measuring the line width, okay, and then kept the temperature of the cryostat constant and just increased it by means of the, let's say, of the presence of this heating source.
I see. And maybe a technical question: how do you collect the the photons? Because you have the membrane, and I will presume that your typical seals that you use.
No. Here there's no seals. We do have a cryostat that allows for a quite high numerical aperture with an objective that has a long working distance and still has a numerical aperture, I would say, of 0.7. And that's enough to collect photons. I was scared too, and that's why I told David, look, it's not obvious that we managed to position a nanocrystal there and that we will get enough light out, and that will still measure narrow lines. And indeed, also because the membranes were made out of silicon, so they could be, however, silicon should not be absorbing at 780 once you are working at 1.4 Kelvin. So that's actually a plus, but obviously there's no efficient photonics redirection in this case.
But you still collect from single molecules.
Yeah. We see this was a single molecule because we really have to measure the line width.
Good.
And we did. I mean, there are many more experiments around it, but I mean, as I said, I would like to organize a dedicated workshop on that. I didn't have time up to now, but I will definitely do that because we have many more experiments about these, for instance, in which we compare what happens to the line width for molecules, for different molecules inside the same nanocrystals. And instead, what happens if you compare molecules in different nanocrystals? Okay.
I see.
Good. I think we have another question by Clivia. Maybe Clivia, you can ask. Yeah, thank you.
Yeah, thank you. That was a great talk. I enjoyed it. I just have a question concerning the zero phonon line in molecules, right? I mean, I think I understand the zero phonon lines in semiconductors and so on, and how they come about from a level of disorder or a level of non-periodicity in the crystal, building the non-zero line as connecting all the way vector case in semiconductors, right? But here you have molecules. So you have different states. So how is the terminology, the concept translated from the usual semiconductor zero phonon lines, films, quantum web?
I mean, molecules are, I mean, in the end are much simpler, right? It's just like an atom. It's just like you have these are just optical transitions similar to atoms. Now, in this case, the fact of having molecules implies that you also have vibrations that are coupled to electronic transitions.
Yes.
And the zero phonon line is the very special case in which you do not couple to any vibrations inside the matrix. Now, if you want to know, I mean, in particular, I mean, the terminology in the case of molecules is that of a transition between let's say the highest occupied molecular orbitals and the lowest unoccupied molecular orbitals, the famous HOMO-LUMO gap. And yeah, what else can I say? I mean, sorry?
Why phonon? Zero phonon line in the name of the transition. It is a direct transition between two electronic states.
No, exactly. These are the zero phonon. I mean, this is the one where you don't have any vibronic coupling. I mean, typically you can have vibronic coupling due to the fact that the electronic distribution in the excited state is different with respect to the ground state, which means that that this can excite the nuclear vibration. Okay, so the equilibrium coordinate of the nuclei is shifted. I mean, this is the standard Frank Condon situation, okay, in which you have this harmonic potential as a function of the nuclei coordinates in the ground and in the electronic state, which is slightly shifted.
The vibrational picture.
Exactly. And this is, let's say, at least the...
Ah, okay, good. Thank you. I didn't know that the terminology was used also for the Q vibrational picture, but that's good. Thank you. I'll say goodbye.
Bye, Clivia. Nice to see you.
Hi.
Bye.
Right, so I don't know if we have any other question. If not, I would really like thank you, Constanza, for the seminar, also for Martin for the short presentation. I hope we meet soon in person, and I thank all the attendees for their attention, and also Clivia for hosting this seminar in the ICN2. So thanks a lot
to everyone.
Thanks a lot.
Thank you.